Ladies and gentlemen, it gives me great pleasure this morning to introduce my colleague from Imperial, Patrick Farrell, who is going to enlighten us on the work he's been doing on automating the process of producing Agile models.
All right, good morning, everyone, and thanks for coming. I know that there's an awful lot of seminars at the Newton Institute, so I appreciate that you came to mine. So I don't really work in the atmosphere or the ocean, so you may be asking, why am I here at this program at all? Well, the point is that I do work on something that is very closely related and very important in the atmosphere and ocean, which is the topic of adjoints. And so I hope today to talk a little bit about my research on adjoints and also to demonstrate some of the applications that we've been using them for in atmospheric and oceanic sciences. So just to be clear, when I talk about optimization, I'm not talking about making your Ford model faster. I'm talking about solving optimization problems subject to PDE constraints, subject to the constraints that the laws of physics hold. And stability analysis, I'm not talking about the stability of your discretization. I'm talking about the stability of physical systems themselves. All right, so I realized that maybe not everyone will know what an adjoint is or why they should care. So I thought I would talk for 10 or 15 minutes about them first. So hopefully this will be 10 or 15 minutes, then about half an hour of my research, and then hopefully 10 or 15 minutes for discussion after. Okay, so this talk, I want to introduce the notation first. And I do this in all my talks, not just the ones where Professor Gunsberger is sitting in the audience. So M here is a bunch of control parameters, right? So this is something that you feed in as input to a PDE. It could be your initial condition, it could be a boundary condition, it could be a diffusivity coefficient, it could even be the shape of your domain in very complicated situations. So we'll have some solution of your PDE U. So in the Navier-Stokes, this might be velocity and pressure, and so on. So all considered as one variable U. So F here is the abstract description of the PDE. So this is a PDE parameterized by our parameters M with solution U. And so we'll assume that it's nice and differentiable, and that for any sensible M that you give me, I can solve it to compute a solution U. So after we've solved our PDE for U, we're actually not interested in the solution itself. We're only interested in one quantity of it, one real number that we will derive from the solution. That real number is encoded as a functional. So this might be the difference between your observations and your computations, measured in some norm. It might be some measure of the engineering quality of your design, like the lift-to-drag ratio of your wing. In general, this is whatever it is that you're interested in. And so a notational convenience, so this J hat is the reduced functional, where we substitute in the PDE solution. So here I've implicitly assumed that for any M you give me, I can compute a U uniquely. And so this computation of U of M involves the PDE solution. But so this is what we actually want to maximize or minimize. And so this is what we're going to need the gradient of later on. And finally, lambda is the adjoint solution. OK, so first off, what is an adjoint, right? What is the adjoint equation? So given a PDE F and a functional J, the adjoint is, so first of all, it's another PDE. This time, it's linear, right? It's a linear PDE that is derived somehow from the original Ford system. So this derived PDE, the adjoint PDE, depends on, well, the structure of the Ford equation, first of all, but also the Ford solution U, because we're going to linearize about that solution, and the functional J. The right-hand side of your adjoint PDE will come from the functional that you're interested in. And also, in the continuous case, the boundary conditions and so on also come from your functional. So in general, it's quite hard to derive. And it's useful for lots and lots and lots of things in computational science. And so basically, if you're ever in a situation where you don't know everything about your system perfectly, the adjoint will probably help you out somehow or other. So over the past few months, I've been building this graph of what an adjoint is useful for. And it's getting to be a bit unwieldy, actually. So you have your Ford simulation. And then from that, we'll derive our adjoint PDE and solve it. And then here are all the things, or even, well, some of the things that you can use adjoints for. So you can use it to estimate errors in your functional computation if you're interested in doing adaptivity or interested in investigating how much of an impact your discretization is made. You can compute gradients of your functional. Sometimes that's just of interest in its own right because it provides physical insight. What's the derivative of the Antarctic circumpolar current with respect to the bathymetry and so on, things like that. So, and with these, you can do all sorts of stuff. You can optimize functionals with respect to your parameters subject to the constraint that the laws of physics hold. You can do stability analysis in a more general and more powerful way than just the traditional Lyapunov eigenvalue analysis. You can do continuation and bifurcation analysis if you're interested in looking at the qualitative behavior of your PDE system. You can do data assimilation, so this is obviously of huge importance in meteorology and oceanography, and so on and so on. So I won't present applications from all of these, mainly because I haven't done them, but I will present 4 applications, one from each of these boxes. Okay, so just to write down, so I won't bother going through the maths of deriving the adjoint PDE, but if you're interested in this, then I'm very happy to talk about it on a blackboard somewhere afterwards. But here it is. So let's just take a look at, and just to understand a little bit about where the properties of the adjoint PDE come from and why it might be hard to compute. So first of all, the right-hand side, let's look at that. So that's the derivative of your functional with respect to its immediate inputs, right, del J, del U. So this is typically very easy to compute. J is normally a one-line analytical expression, and so you can differentiate it on paper and then code it up, so it's not a big deal. So F was our original PDE, and del F del U is the linearization of that PDE operator about the forward solution that we computed. So far, that maybe not so bad. The really hard part, where the interesting thing is when you take the adjoint of that linearized system. That's where the word adjoint comes from. It's the adjoint of the tangent linear system. And so this is what causes an awful lot of computational difficulties in deriving, assembling, and computing efficiently with the adjoint. So first of all, the adjoint equation is linear because we've linearized a PDE operator. So del F del U is linear, so del F del U transpose is also linear. And it depends on U. So what that means is that in the adjoint computation, we're going to need to have available the forward trajectory that we solved for in the first place. Right? Normally, when you're solving a forward model, you just solve for this time step, you move on, you forget as much as you can, you advance, you forget as much as you can, and so on. Here, we're going to need some way during the adjoint computation to access the forward variables that we computed. So we can't throw them away completely. And so the adjoint equation is solved backwards in time, so upper triangular. So the reason for this is it comes from the transpose of your linearized system. Right? So the linearized system, so your forward system is lower triangular. It propagates forward in time. Given the solution at time 0, you can compute the solution at time 1, and with that, the solution at time 2, and so on and so on. So there's a temporal propagation of information forward in time. But when you take the transpose of a lower triangular system, you get an upper triangular system. And so what that means is that the adjoint runs backwards in time. So if you do the analysis at the continuous level, what it turns out is you get a terminal condition on your adjoint PDE, and then you're solving for as a prognostic variable all the way backwards to the adjoint associated with your initial condition. And so what that means is actually this is what makes the access of the forward solution quite difficult, because we're going to need to keep the first solution all the way forwards and all the way backwards, and we're going to need to be able to access that solution. So anyway, so once you've assembled and solved this somehow, which is what I'm going to talk about, then you compute the functional gradient using this simple formula. And just to get across the reason why people care about adjoints for functionals. So you'll notice that this adjoint PDE, it depends on your functional, so J shows up, but M doesn't show up at all. Right? There's no M in this adjoint PDE. So you can solve the adjoint without any reference to any parameter. You don't even need a parameter if you're not doing an optimization problem. But then you can compute this very, very easily for any particular M. So what that means is that once you solve the adjoint equation once, you can compute this gradient very, very cheaply, no matter how many M's you have. So this is of enormous interest when the size, the space of your control parameters is very large. Like if it's an initial condition for your atmosphere and your ocean, then it might be 10 to the 8, 10 to the 10 numbers in this vector of control parameters. And you can't compute a gradient if you have to do a number of PDE solves that's proportional to the size of that control space. Whereas the adjoint is only proportional to the number of outputs. And if you only have one output, then that's extremely efficient.
So what if the system is irreversible in time? You have to assume something, right?
So I'm going to take the lazy man's approach from the analysis and assume that everything is nice and differentiable and so on and so on. If the system forgets information, like if you have a parabolic system that loses the initial condition, well then you'll just get the fact that the gradient is 0, right? So the adjoint will decay to 0 to reflect the fact that the influence propagating backwards in time is 0. So, but all of these derivatives exist, they just might be trivial.
Well, a hard problem if you're doing 4D var, say things like cloud, which can just suddenly disappear, and you have no knowledge that you're near a state with cloud with a derivative, can't see it, and that's just a fundamental limitation of just using a linear approximation. You can't get around that.
So we'll just, there may be lots of problems where this isn't applicable, but there are many, many problems where it is.
You know, it's,
So-
it's extremely helpful, but there's some things you can't. You have to realise there's some things you can't do, and just accept that and find other ways of doing it.
Yeah, absolutely.
I understand why you say things disappear, because the adjoint relies on the whole forward history. So everything that happened forward will go into the coefficients of the adjoint equation. So,
I mean, so if you had a parabolic system that forgets its initial conditions, then the adjoint solution will decay to zero as you return backwards towards the initial condition, because, at least that's my intuitive guess, because the influence of that
yeah,
initial
but,
condition.
well, it does that, but it's not because, but it doesn't forget the fact that there's an initial condition for
Oh
the
yeah,
state.
absolutely. It's just the influence on the output is forgotten. So as an example of the kinds of problems that we're interested in, so this is an example of a PDE constraint optimization problem that we're very interested in from a marine engineering point of view. So the problem is the following. So here is a channel, and you've got a tidal flow coming in from left to right. And what you want to do is you want to place turbines in the flow in order to extract energy, to generate electricity. So this is very much like wind turbines, but in the sea. So each of these black dots will be a turbine. And so what we now have is the parameters are the positions of these turbines, the positions of the black dots. And what we would like to do is maximize the power that we produce. And depending on the geometry of your system, if you have islands and channels and all sorts of things, then you could imagine that this gets very complicated, especially because in engineering practice, we'll probably want to deploy about 500 turbines in a particular site. So this is a rather large control space of about 1,000 degrees of freedom. And so if you were trying to optimize this problem without any derivative information, it would be quite difficult. So here's linear shallow water equations, but we actually solved the nonlinear ones. And so we're going to compute the derivative of the power with respect to the positions. And so I'll show an example of this later on. Okay, so does this matter? So there's a nice book by Uwe Naumann who's talking about algorithmic differentiation that was published by SIAM at the end of last year. And in the introduction, there's a nice quote that says, the automatic generation of optimal adjoint versions of large-scale simulation code is one of the great open challenges in the field of high-performance scientific computing. So this might be particularly grand, and but it's nice that someone else says that the problem you work on is actually interesting and important. And so this is the problem that I'm trying to solve in this work, in this talk, for finite elements. Okay, so that's the end of the brief introduction to adjoints and why one might care. All right, so on to the talk about what I've done particularly. So before I introduce what I've done, I just want to mention very briefly the traditional approach to deriving adjoint systems, at least all in the discrete case. I won't talk at all about continuous adjoints. Okay, so we always start with these diagrams in the top left, right? So in the top left box, we have our discrete forward equations written down on paper, right? So you've taken your PDE, you've applied some discretization that you like, and now you have it written down. Okay, so then you supply those equations to your PhD student or your postdoc, and he goes off for a year and implements the model in 100,000 lines of Fortran or C++ or whatever it is that you like. And so you end up with a forward code written in some language like Fortran or C++. And now you decide, oh, I want to differentiate this, I want to have an adjoint. And so then you turn to the traditional tool, which was to help the creation of adjoint models, which is algorithmic differentiation. So algorithmic differentiation fundamentally is something that takes in a forward code and gives you an adjoint code. So this would be 100,000 lines of Fortran, and now this is 200,000 lines of Fortran. Okay? And this has been on the go now for 30 or 40 years, and there are some major successes, don't get me wrong. For example, the MIT Ocean model is differentiated this way. They use TAP for their algorithmic differentiation. But it suffers from some major limitations, as I'll talk about. So just to focus briefly on what algorithmic differentiation is, the fundamental idea is that we're going to use the chain rule. Right? Familiar to everybody, I hope. So a model is a sequence of elementary instructions, whatever elementary instructions means. Differentiate each in turn, and then compose with the chain rule. Right? So by elementary, I mean simple enough to differentiate individually, and then we'll just compose the derivatives with the chain rule. So even if your computation runs for weeks and is extremely complicated and runs on 100,000 processors, fundamentally, you've just done a sequence of instructions that map from your input all the way through to your output. It might be trillions of instructions long, but it's still just a sequence of instructions, and we can differentiate through it with a chain rule mechanically. So in most tools, elementary instructions means the simple functions that appear in your language: addition, subtraction, multiplication, take a sign, take an exponential, things like that. Okay, so that sounds great, and it does work. There's some major successes. But in practice, they're extremely difficult to use. And so my hypothesis, my theory for why this is the case, is that the numerical intent of the program that's expressed in your source code, that stream of instructions that you want to differentiate, is jumbled up with all sorts of implementation details. Right? Your source code is a lot more than just that. There's a whole load of things about how you want stuff to be implemented that isn't really relevant for the adjoint computation that gets in the way. So things like pointers and aliasing. AD tools have to worry about, these two expressions don't look the same, but they actually refer to the same variable because you've taken a pointer in some other routine in some other file. Expressions with side effects. Again, you have to differentiate through this. Preprocessor directives, parallel directives. The code is jumbled up with calls to MPI, directives OpenMP, all this sort of stuff. And handling all of these things that come with the stream of numerical instructions is normally what makes differentiating codes with AD quite hard. So the drawbacks of this approach, so it's a major investment of labor. So they've stopped calling it automatic differentiation now because it's not really fair. So they refer to it as semi-automatic or algorithmic differentiation. So it doesn't work naturally in parallel. So I was at the AD conference in Colorado in July, and one of the major research topics at the moment is how do you automatically derive parallel adjoints? Because you want to solve big problems and you need to run in parallel. But you have to reverse the control flow of all your MPI communications, right? Sends become receives, and receives become sends when you take the transpose. So the adjoint derived can be extremely slow. So Naumann, in that same book, describes the typical factor of slowdown as between 3 and 30. And checkpointing requires large amounts of intervention. So, please.
Oh, no, go ahead. So I was just going to say, what about the alternative of, the adjoint is already an approximation. It's a linearization. So instead of writing the forward code and then applying AD to it, why not just write down the adjoint, right, and discretize that just like you did the forward model, right? It doesn't have to, the adjoint doesn't have to be an exact representation of the forward model. It just has to be a good approximation.
Yeah, I completely agree, and lots of people do that and prefer continuous adjoints for one reason or another. The main problem with that, I suppose, is that now you have to write 2 models instead of 1 model. So you've doubled the amount of human effort of labor that's involved. And if your model development is slow or complex or expensive, which it typically is for lots of real systems, then that is a problem that you can't just derive the adjoint really easily and then apply it to some problem. That it's a major investment.
But have you really doubled it? I mean, isn't a lot of the operators that you wrote for the forward model reusable in the adjoint?
A lot of the infrastructure underneath for expressing your finite volume or finite element computations. But in practice, people who actually do this have to be very well financed with large teams of experts that can handle these sorts of things. And it is, it's certainly possible, and for someone like the Met Office, it's entirely possible. But it's a non-trivial effort.
I was going to say, in our experience, what we did is we linearized the model, and there we were selective about which terms we included, because we said, well, some of those terms, if you formally linearize everything, you get huge numbers of terms. It's very expensive with your. So we were very selective about that, but we found that if you want to make our minimization converge, the adjoint really did have to be the exact adjoint of that linear model. So when we do an iteration going forward and back, it's not, for instance, we have an elliptic solver in this loop, and we solve the adjoint problem using an elliptic solver, and we have to solve it much better than you would expect, or else the adjoint is not sufficiently accurately the adjoint of the linear model. Otherwise, it doesn't converge. So that's you have to be quite strict about that bit, but you can take a physically informed linearization of your nonlinear model and leave out a lot of things that don't really matter, and use cheaper algorithms for some of it as well. So there's a great scope. So I would never want to do a formal linearization of our code, but I would have to be strict. We always have to be strict about the adjoint of that linearization. That's what you think as well, Nielsen?
Yeah, it's a video. What you say with the operators is true. And we use, for example, the spectral transforms in the same way as before. So, things like that, you don't have to redevelop, basically. You just want to, you have to obviously be careful with the linearization of the model. And part of the way it works at ECMW is, in fact, when you now develop a piece of code in the dynamics or in the physics, for that matter, immediately that person is tasked with having to write the adjoint as well, which is a pain, I must admit, but that's the way it is.
First of all, the adjoint equations contain no approximation. They're linear not because something is being linearized. That's what comes out of the Lagrange multiplier rule, the linear equation. So there's no approximation in the adjoint equations.
Okay. Assuming that you can find them.
Right, right. So, but, you know, in our experience, there are problems where you can get pretty gross approximations to the adjoint, but there are problems where the adjoint actually has to be approximated better than the forward model. So it depends on the what the application is.
Also, a comment on the continuous adjoint, deriving the adjoint and then discretizing it exactly the same way you do the forward problem. We had a bunch of very strange experiences because the truncation error of the forward problem is not necessarily adjoint to the truncation error of the backward problem. So if there's no inherent damping in your equations, you can get a lot of surprises where the whole code blows up because the truncation error, as you iterate back and forth, gets just amplified every time, forward and backward. So a continuous adjoint discretizing with the same technique as the forward is sometimes a little bit dangerous. So just throwing that in as a
No, I'd like to talk to you about that
experience,
afterwards, actually.
and that's why we usually go towards discrete adjoints, where it's a true adjoint.
But I think this is a religious war. It's like Y versus Emacs.
I didn't mean to step into it.
Yeah, go ahead. Okay, and so implementing a checkpointing scheme requires large amounts of intervention. So for example, if you look at the source code of the MIT Ocean model, there are thousands of directives added by hand to say store this, recompute this, and so on. And that's a major pain, and B, when you have to do that much work, it's very hard to do it optimally, right? To minimize the amount of recomputation in your backwards through different configurations. However, having spent a few minutes talking about why I don't like AD, I should say that it's great, right? It's much easier than doing it by hand, and there are people who solve problems that they can't solve without AD, right? The MIT Ocean model is a great success. And all of the above problems can be solved with effort, right? This isn't about doing something that can never be done before, it's about doing something that's previously extremely expensive and doing it easily. Okay, so onto the approach that I want to talk about. So here again, we're going to start in the top left box, but instead of just writing the equations, the discrete forward equations on paper, what we're going to do is we're going to have a language for expressing the discrete problem, the discretization that we want to solve. So we're going to have some language, it's called UFL, and it's for expressing variational problems. So this work is specific to variational discretizations, in particular finite elements. So anyway, so once we have this representation, we're going to pass it to a special compiler. So the compiler is taken from the Phoenix system, which is developed at Simula in Oslo. And so what they do is this compiler will take your symbolic representation of your equations and generate the code that's specific to those equations. So for the assembly of the matrix on the right-hand side, that's specific to this PDE system. So just as no one writes assembly code anymore, and they've raised the level of abstraction, and now everyone writes C++ and lets the compiler handle the machine-specific details. So what I think my interpretation of what they're trying to do is you write down the PDE that you want to solve, and then you let a compiler take care of the implementation details for a particular system. So this all already exists and has been developed for about 10 years now, including by Garth, who's sitting in the audience. And so what I've done, so in my work, is implemented a symbolic manipulation system. So to analyze this sequence of discrete forward equations and produce from them the sequence of discrete adjoint equations. And so the reason why this is possible is because we have a symbolic representation of the equations as data here in the top left. And so we can manipulate them in some sort of symbolic way to derive the discrete adjoint equations. And once we have them represented in the same symbolic form, we supply them to the same compiler to emit the adjoint. So rather than going from here to here and then taking the adjoint of the code, we'll take the adjoint of the discretization. So all of this is discrete adjoints, and it's still discretely consistent. But we differentiate on this level and then pass over to the implementation with the same system. So just to give you an idea of what does this symbolic representation look like, so here's the Burger's equation in maths. So the time derivative, then we have an advection term and a diffusion term. And if you write this down in the language UFL that all of my problems are expressed in, then this is what it looks like. So you have so the time derivative is this one, then u star grad u, and then v is your test function in finite elements. So there's our advection term, and then here is the diffusion term integrated by parts. So the gradient of the test function and the gradient of the trial function multiplied by the coefficient. And so as you can see, the language in which you express your problem in code, so this is code, is almost isomorphic to the language in which you express your problem on paper, right? which is really, really nice. And that's what makes all of this possible. So the fundamental idea, the fundamental abstractions that I take in my approach are that a model is a sequence of equation solves. So rather than just treating a model as a sequence of elementary instructions, we're going to raise the level of abstraction much, much higher. Still the same structure, a model is a sequence of something, but treat it as a model as a sequence of equation solves rather than elementary instructions. And that way we're going to cut out all of the numerical implementation difficulties that make AD hard. So we're going to differentiate each of these equation solves in turn and compose with a chain rule. And the fundamental idea, at least Garth might have a different interpretation, but for me the fundamental idea of Phenix is to represent the equations to be solved as data, and then use a compiler to generate the details for that. Just express your problem, and then make it happen. Okay, so just to give you a more concrete idea of what this looks like. So here on the left-hand side, we have the entire code for the Burgers equation. Nothing's been taken out. So this is a time-dependent nonlinear solver. It'll use Newton iteration to solve the nonlinear problem at each time step. So the core line here is this setup of your form f. So here is an expression of the variational problem that's specific to the Burgers equation. If you wanted to change to a different PDE, then this is the part that you would change. So here you have your time term, your advection term, and your diffusion term is normal. And so on the right, here is the adjoint version with the library that I've written. And I hope you agree that it's fairly compact and fairly easy to understand. So we import the library at the start. And then here we set up a functional, which is the L2 norm squared of the velocity evaluated at the end of time. So inner means the inner product, and star dx means integrate over space. And then we just take the derivative, compute the gradient of j with respect to the initial condition of your velocity, and that's it.
So are you using some computer algebra systems?
And no, this is implemented in by me. So this isn't based on.
Well, yes, in the sense that UFL is a computer algorithm.
Well, yeah, it's pretty. Yeah. So the symbolic manipulation it sequences a stream of instructions, and then the UFL implements those.
But you are assuming certain type of differencing. So does it mean that each time you change differencing, you have to change adjoint as well, or it will be done automatically?
So it'll be done automatically. So the way that this works is that when you import this library, it overloads the calls to solve, and for everything that solves equations or changes variables. And what it does here is it records the equation that you described as a sequence of equation solves, and then differentiates that. So if you change something up here, if you change your time discretization or your spatial discretization or the form that of the equation that you're solving, then that will all be recorded and it will all be changed consistently. So if you change the forward model, there's nothing about the forward model that shows up. You just have to import the library and use it essentially in the ideal case, which is the common. Okay, so some advantages of this approach. So the adjoint derivation is almost totally automatic. I mean, I had to add 3 lines of code in the example that I showed you before, but I hope you agree that it's not too bad. So the adjoint is extremely efficient. In many cases, it approaches optimal theoretical efficiency, as I'll show in the examples later on. So the adjoint can automatically use checkpointing. So in particular, because we have symbolic information about the structure of the equations and the temporal propagation of information, we can automatically derive the optimal checkpointing scheme using the revolve library that absolutely minimizes the recomputation costs for a given amount of resources. So this is, again, a major advantage if you're trying to solve real problems. And the adjoint works naturally in parallel. So both MPI and OpenMP. Whatever runs in parallel and forward will also run in parallel backwards, which is a major advantage of RAID. So the reason why this parallel works, so if you go back to how the system works, so the parallelism, if you write down your equations on paper, there's no discussion of MPI or OpenMP there. The parallelism comes in during the implementation, in the translation from your symbolic equations on paper to the C++ or Fortran code that you've actually written. Right? So the parallelism comes in the motion from left to right. So if you try to adjoin at this level, once you have a code, then you have to deal with all of the parallel stuff that you put in, all the OpenMP directives and MPI calls and so on. Whereas if you derive it on the symbolic level, and then you pass it to the same compiler, well, the compiler knows how to emit parallel implementations, and so it can emit a parallel implementation of your adjoint code in particular. And so whatever can run in parallel and forward, it can also run in parallel and adjoint, which is a major advantage. So some of the skeletons in the closet, so the disadvantages, and in particular for this community, I accept that a lot of these disadvantages will be fatal, but I want to be upfront about it. So the problem must be representable in the high-level language. So if you cannot express your discretization in the abstraction that I've taken, then I can't help you. But the good side is that very many problems can be represented. And I'll show a list of some of the problems that we've tackled later on. So it doesn't apply to legacy code. It's not like AD, where whatever code you've spent the past 10 years writing, I'll take it and differentiate it. You have to express the problem in this high-level system because the symbolic information isn't there in your 100,000 lines of Fortran that you spent the past 10 years writing. However, at least if you're doing a finite element problem, re-implementing a finite element discretization of something is actually really easy. It takes on the order of days. Even so that there is an example of, in the finite element model written in Fortran that we developed at Imperial, there were 3 people that spent a year implementing the Stokes equations, discretization of the Stokes equations for matter convection. And so I went to their office and asked them for the variational forms and got all the data and so on. And I had the same model written in 3 days because I was able to express it at a much higher level. So currently there are no trapdoors for parameterizations because I haven't really been interested in problems where parameterizations matter, but that could be added. And some forward optimizations, in particular some important forward optimizations, aren't carried through to the adjoint. So if you use those optimizations like pre-assembly, then the adjoint is relatively slower. But that's just a problem of software engineering. We haven't got around to it yet. It's not fundamental. Okay, on to some examples. So here's the Cahn-Hilliard system. The solver was written by Garth. And I like this for several reasons. So first of all, it's just quite an interesting problem. It's nonlinear, it's time-dependent, it's 4th order. So in practice, what that means is that it's 2 coupled 2nd-order equations. So we're going to run the problem in parallel over 8 processors over MPI, just because we can. And checkpointing in this case is necessary because I use a very, very fine mesh, and so I'm not able to store all of the solutions through time. So I'm going to impose that I can store 5 checkpoints in memory and 10 on disk, and then the system will automatically use these resources in the optimal way to minimize the recomputation. So just to sort of get across the idea that it's not just trivial functionals like the L2 number at the end of time. So here is the Wilmore functional. So I was Googling around for Cahn-Hilliard functional. And this paper says in the abstract that this functional is intimately connected to the finite time stability of transition solutions of the Cahn-Hilliard equation. So I don't really mind what that means, but I just accept that it's physically relevant. And so this is the functional that we'll use. And so here I'm just computing the gradient of that functional with the adjoint. So I'm not optimizing anything or doing anything. I'm just computing the gradient just to check that it works. And so ignore all the numbers, they don't matter. The important point is the order here. So if your gradient is correct, if it's consistent, then this number will be 2. If it's not correct, if it's not consistent, then that number won't be 2, and this number is indeed 2. So the adjoint derivation is correct. And I check this for every PD system, and it always comes out fine. So, and more importantly, or just as importantly, it gets it efficiently. So the way that in the AD community that the efficiency of adjoints is measured, so you always have to run the forward model to compute the adjoint. So you can never run the adjoint independently. So you time forward plus adjoint divided by forward. So here the forward plus adjoint divided by forward is 1.22 times the cost of the forward system, which is pretty good. And the reason why this is 0.2, so the forward system uses Newton iteration to solve the nonlinear problem at each time step. And on average, that takes 5 linear solves. But because the adjoint PDE is a linearization, so on the backwards runner, we can swap those 5 PDE solves inside the inner loop of the Newton iteration for 1 on the way back. And so if you're just counting PDE solves, then you hope the adjoint will be 5 times faster. And indeed it is.
Linear solves and PDE solves.
Sorry. Yeah, if you're just counting linear solves, you would hope that the adjoint is about 5 times faster, which it is. The adjoint cost is 0.22. So that's great. So on to some more interesting things that we actually use it for. So here's one example of the optimal placement of tidal turbines. So we've been doing a lot of this work in collaboration with Meijin and Rolls-Royce. So here, so the red dots are turbines, and they're constrained to lie within this box, the bounding box. And so after however many 100 iterations, so this is the optimal configuration that it's found, and you see that it's built these barriers to try to trap as much of the flow and to try to extract as much energy as it can. And so here's a plot of the power measured in megawatts as a function of iteration, and you see that it's converged. So I mean, I can't guarantee that this is the optimal configuration, but this configuration, at least however relevant the forward system is, however realistic the forward equation is, and that's the most important thing, but with respect to that, it's a significant improvement in power extracted. So if you can even improve the energy extracted by one of these sites by 10%, then they're laughing. I mean, this is really a fantastic result. So they're very excited about it. And so just to get across sort of the core lines of code that actually make this happen. So up above, we've run the model once to build this annotation to record the sequence of equation solves, the structure of the problem. And so the power is expressed as it's some drag coefficient times the cube of the velocity integrated over space and time. And so our parameter is the turbine drag, and that's what we're changing, or what actually it should be the turbine position. And then so we create the reduce functional and maximize it. And so there's extra arguments to all of these, but this is the core idea. It's really sort of to express it on that level. So a simple example of a data simulation, a very trivial sort of data simulation problem. So this is an idealized reconstruction of a tsunami wave. So here is satellite footage of a real tsunami. So here's the coast before the wave came. Here's the coast after the wave came, and you can see that these areas here are inundated. And so then someone's done some image processing to identify the wet-dry front. Where has the wave actually come? And so the question is it possible to reconstruct the signal that came in from the left from say, a sequence of such images? Right? So we have observations of the wet-dry front, and is it possible to actually reconstruct the tsunami wave? So here's the input tsunami wave. So this, I should say, I have a movie of the forward simulation. So here the wave is coming in on the left, and then so this is the Hokkaido, Nansen, Oki tsunami in 1993. Well, this is actually a lab scale reconstruction of that one, where they saw run-up heights of about 30 meters on the island, which was quite devastating, actually. So here's the input signal. So we run the forward model once to generate the observations of the wet-dry front, and then we don't add any noise, so this is perfect observation, so this is cheating a little. So then we forget the initial condition completely and start from scratch, and then we run an optimization problem to try to reconstruct the tsunami wave, and sure enough we get a pretty good fit. And here's the L2 norm of the observation error as a function of iteration. So it's coming along nicely. And then what does this problem actually look like in the code? So again, it's expressed at a very, very high level. So you describe the functional that you're interested in, which is the observation error between the computations and the observations of your wet-dry front. And then the parameter is the signal that forced it on the left-hand side. And then we want to minimize that functional with respect to those parameters. So on to some other applications of adjoints. So here's generalized stability theory. So this is looking at optimal perturbations to initial conditions to try to explore as much of your state space as possible. It's quite important in data simulation, in ensemble methods, and these kinds of things. So suppose that you're interested in, let's say, initial conditions, but it's not specific to initial conditions. So if I give you an initial condition, what small perturbations, delta m, grow the most over some finite time window? We have a forecast window, and I'm not sure about my initial condition. I don't know what it is exactly. But so I'm willing to sort of allow some perturbations around it, and then I'd like to see where can those perturbations lead me. Will it lead to somewhere completely different, or will it sort of mostly be the same? So if you grind through the mathematics, you end up that the answer is the solution of this singular value problem. So it's the singular vectors of this thing called the propagator, which is essentially the inverse of the tensor linear model, with some other matrices around it. And so we'd like to compute these singular vectors. So there was a PhD student at MIT, Lorzana, who's in a lecturer at Oxford. And her PhD was on doing this computation with the MIT Ocean model, which had an adjoint and a tangent linear system. But essentially, in order to rig all of the software up to derive the tangent linear model, to derive the adjoint model, to hook it all up inside some sort of iteration to compute the eigenvectors, took her years. And that was the meat of her PhD. Whereas now we can express these sorts of problems and have them solved in a day or so. So here's it applied to something vaguely oceanographic, so salt fingering. So here is the perturbed interface. So this is, I forget. So this is a configuration from a paper in 1998, but I forget who by. I think it was Gochman. And so he suggested this perturbation and then gave some reference data for what your solution should look like. Treating it as a test case for this kind of model. And someone in our group tried to reproduce this and couldn't. No matter how they fiddled with it, they couldn't get the fingers to look the same as it did in the paper. And so sure enough, so then I started investigating. And so it turns out that there are very small perturbations that you can make to this initial condition, so secondary perturbations, that change the simulation significantly by sort of, in an L2 norm, by a factor of 10,000 or so. So you can see that this perturbation, even when it's extremely small, promotes the growth of some fingers and retards the growth of others. So you won't get this nice uniformity the way that it's imported. So if you use a mesh that's more or less in any way different from the one that was used in the paper, well then you are going to excite some of these perturbations somehow, and there's lots of them. So you can't really expect to get this symmetry if you do this in a general case. And so again, what does the code look like? So here it's really just one line. So the propagator is defined to be mapping from initial salinity to final salinity, and we ask for 10 singular vectors. And then it will go off. So this one call will go and derive the tangent linear model, derive the adjoint model, hook them up, and so build a matrix-free representation of the action of the propagator, and then hook that inside an eigenvalue computation, all running in parallel to compute the singular vector. Okay, so we've been doing this since about December now, January maybe. And so over the course of this time, I've applied it to lots of different PDEs, just to sort of check that it works and to show its generality. So in the repository, there's all sorts of applications. The Burger's equations, Navier-Stokes, Stokes plus nonlinear rheology for mantle convection, the shallow water equations, Cahn-Hilliard, the Gray-Scott. On Friday, I did the shallow ice equations, the Gross-Pedievsky equations from quantum mechanics, the Mabi problem from general relativity, and so on and so on. So this does work for lots of real problems if you use the finite element discretization that we can express in the nice high-level system. So in conclusion, so the aim is to totally automate the computation of the adjoint and to partially automate its uses. I don't think you'll ever automate the solution of a PDE-constrained optimization problem because it's quite difficult. But you can certainly give all the ingredients and have a button that someone can press go and configure as appropriate. And the code is still under a lot of development, but it really works for a lot of useful cases. And so the future work, so I want to do some reduced order modeling to improve the optimization, the speeds of the optimization further, looking at deriving the second order, actually that should be the tangent quadratic, the second order adjoint equations, doing some more PDE constraint optimization, using the adjoints for goal-based adaptivity, doing some continuation and bifurcation analysis, and ultimately applications, because this is sort of where the interesting part is. So that's the name of the software, Dolphin Adjoint, and here's the website that I set up, and it's all released as open source. And that's it. Thanks. So here are some, well, I'm sure that people have things to say, but here's some things that I wanted to talk about. So the first one is, why are adjoints not used more commonly in computational practice? Right? So in oceanography and meteorology, people tend to know what adjoints are, but in lots of other fields, they don't. And so my hypothesis is, my feeling is that it's the difficulty of deriving them, but maybe people have other suggestions. I was hoping that Hilary would be here because I wanted to ask her if OpenFOAM was sufficiently high level to apply something similar, because the fundamental idea isn't specific to finite elements, it's just that there's a nice high level system to express finite element discretizations that's amenable to symbolic analysis. If you had a finite volume or finite difference system that expressed the same at the same high level that was amenable to symbolic analysis, then you could apply the exact same technique. And is anyone interested in developing or using an adjoint of some PDE? So I'm here until the end of November. So, great, thanks.
I had a question about your turbine. Can you flip back to the? So you have specified inlet conditions?
Yes, so this is just steady flow with an inlet going from...
So a certain amount of volume flux is specified, and you have no normal at the lateral
Yes,
boundary?
I believe that's the boundary condition. So this was run by my colleague, Simon Focus, so I'm not... He'll be here in the middle of November if you want to grill him on the exact details of the discrete.
I'm wondering what sets the scale of the width of the turbine from the lateral boundary? I almost wonder if there isn't some sort of penalty? I mean, because if you're specifying a constant vertical flux, I think the solution is you stack all of the turbines directly across.
Yes, you're dead right, but there's a constraint imposed, so the turbines cannot leave the bounding box of the original setup. So in real life, they buy licenses for certain sites, and so they're very strictly limited to sometimes quite awkwardly shaped domains. And then there's all sorts of other constraints on the bathymetry, so they can't deploy it if it's too deep or too shallow. So actually, even though you'd like to just block the whole channel and forget about the ships, and then you can generate an awful lot of power, in practice you can't do it that way. So we wanted to add some sort of realism. I should emphasize that although these are idealized, this is one idealized case, we are actually doing this now in the inner sound, in the Pendle and Firth, in real geometry with time-dependent tidal flow going back and forth around in shallow water. But we're not really allowed to show this because it uses commercial data and stuff.
Thanks.
So can you deal with, or will you be able to deal with different grids for the forward and adjoint?
I could do. At the moment, you don't, but it would be a fairly straightforward thing to add a hatch to say that I want to increase the order of the discretization of the adjoint equation, or I want to solve it on this mesh rather than another. Because it would just be at the symbolic level of the adjoint equations, you just pluck out the function space that you operate on and replace it for another function space. So it hasn't been done, but in principle, that's pretty straightforward. Because I know that's important for several different systems where you want to solve the adjoint in a different manner.
Trigger, I'm interested in your example for the tsunami case, obviously. So you showed as a motivation this picture, which in a way, where you kind of argued that you wanted to invert to the source from the inundation pattern. Did you really do that with your example?
No. So I mean, this is real data, and this is idealized real data.
Did you take as for data? Did you take the inundation data, or did you take the gauge data that is provided in the water? Because I wonder how you do it actually, because inundation is flip-flop, right? It's digital. Either you have inundation or not. How can you take any derivative of that?
So, well, that's a very good point. And I mean, a wetting and drying scheme generally has lots of non-differentiable switches and so on. So I should say that this uses the wetting and drying scheme that was developed in Louvain-la-Neuve. So Kainer, I think it's the name. And so what we did was, and I think in their wetting and drying paper as well, they replaced all of the non-differentiable operators, the mins and the maxes and so on, with smooth variance. So you have some parameter alpha, and if alpha is 0, then it's the same as the max. But if alpha is not 0, then it's not really the max. It's some sort of smooth max. And so then all of the operators become differentiable or forced to be differentiable. So this wasn't really, I mean, I'm not really claiming that this is the inversion of a tsunami wave. There's a huge amount of work to do to actually make sure that with these smoothed operators that it's still physically relevant and to actually get it to work for real data. But it was just to show the proof of concept. Because as far as I know, no one's done anything on adjoints for wetting and drying. So I think this actually is the first one. If someone knows otherwise, then please tell me. So I think even sort of making that first step is quite interesting.
Could you repeat last sentence? You are not aware about anybody doing adjoints with what?
Wetting and drying. So I don't know of any, but there might.
Paper coming in JCP by Bless, Sansir, and Mavriplis. They are doing tsunami prediction and using adjoints.
So is that published, or were you reviewing?
It's in those online already.
Okay, great. I'll take a look. Yeah, thanks.
I come from different community where we use adjoint equations, for example, for shape optimization. And one of the problems is that when you derive adjoint equations, there are lots of difficulties when you start to have more and more constraint imposed during derivation. Is there anything which helps with additional constraints in your method, or your constraint is in minimization is basically the governing equation? But if you start to have, let's say, you mentioned some constraints in the example. Is there anything which you?
Yeah, so you can impose bound constraints, equality constraints, inequality constraints on your controls. State constraints are a bit harder to deal with, so we haven't done that far yet. But so basically you pass extra arguments to the minimize or maximize routine to express the constraints that you want to impose. I mean, sometimes constraints make your optimization problem easier, right? Because it only has so much less to explore. You know? Whereas other times, maybe it makes a problem infeasible, or maybe there's no solution. But I mean, that's not something that I can help with. Right?
There's no new maths here, right? An important point here is that there's absolutely zero contribution here.
Thanks.
Sorry, can I finish the sentence? I'm not going to.
But it just makes it easier to achieve.
The numerics of optimization or adjointing. What the contribution here is that the process is made automatic and efficient by expressing it in a much more mathematical way and a much higher level way.
Yeah, this is more of a computational science exercise than an optimization research or something.
So in principle, everything you can do with this, you could have done the other way if you have an army of gnomes somewhere prepared to do the massive amounts of work to do it. But actually, in reality, things that were either totally infeasible or infeasible unless you happen to have a national lab lying around to do it with, suddenly become much more tractable. And that's the big story.
How do you validate the adjoint model?
Sorry, say again, please.
I want to know about how do you validate an outcome? Like your model is given and you get an adjoint.
So the main tool for verifying
Another adjoint?
So the main tool for verifying the adjoint computation is this Taylor test. So what we do is, so you have some functional of some input, right? So here's a functional and here's an initial condition, and you perturb the input. And so if you just take these terms, well then by the Taylor series, that should converge at first order as your perturbation goes to 0, right? And so that's indeed what you see. You see that this expression converges at first order. But if you add the next term along in the Taylor expansion, the gradient, well then now this in maths should converge at second order. But if your gradient is not consistent with what your Ford model is actually doing, then it won't be second order. So it's actually an extremely sensitive test. Convergence orders in general are generally very sensitive tests. And so if these numbers come out to be 2, then you can be more or less very confident that your adjoint is correct. So I wouldn't say you validate it because it's a verification exercise. It's checking that the adjoint is really the adjoint of the Ford system that you've implemented. But if your Ford system is relevant to some real system out in the real world, well then the adjoint will also be relevant to that. So this is purely adjoint to Ford model verification. Validation is a different step.
In aeroacoustics application, we often need sponge layers around certain parts of the domain that damp out the acoustic waves as they go out and avoid reflection on the boundary. How would your adjoint code generation deal with that?
Well, so presumably how that's expressed is an extra term in your source term, right? You have some source or absorption term. So it just shows up in the variational form of the problem that you describe in that F. And so then it's all handled in exactly the same way.
But as the flow reverses, the sponge layers are in the wrong spot.
Well, so in general, I mean, this is an important point about discrete adjoints, that if you have lots of computational facilitators that are tricks or hacks to try to get the Ford model to work for some real problem, you probably don't want to adjoint these.
We do want to adjoint.
Well, then if you add to the variational form, then it'll just happen. But if you want to impose the same thing but to your adjoint PDE, well then none of this is handled at the moment. But it entirely could be. Sorry, you had something to say?
I think you made my point that that if you have computational facilitators like limiters, like sponge layers, I mean inflows become outflows and vice versa in the adjoint. So then any kind of thing that uses a discretized code to produce adjoints is going to do that. And same thing with turbulence models, which I also view as a computational facilitator. They're all going to be differentiated. I mean, they're all going to be used, and you may want to develop different computational facilitators for the adjoint. That's the one thing you can say in defense of continuous adjoint.
absolutely. So if that's the case where it's really crucial for you, then you should probably use continuous adjoint. But I mean, a lot of these same ideas about expressing the problem at a high level and then differentiating it. You could imagine, so all of this was discretely consistent, but you could imagine expressing your continuous problem, sort of if you didn't specify a spatial discretization, and you expressed your time discretization in some sort of symbolic way, and then applying a symbolic manipulation to derive the continuous adjoint equations as well, which is often a major pain.
Would it be possible to do something like stripping the forward model of all facilitators,
Yes,
and
it
then
could be,
deriving the
yeah.
adjoint for that, and then adding adjoint facilitators?
Assuming that that would require user intervention to mark the facilitators.
What's that?
It would require user intervention to mark the facilitators, because
Yeah.
the automated system is incapable of working
Sure,
out
sure,
whether
of course.
that turbulence model is in some sense real or whether it's there to stop you crashing.
Yes,
So you've got
yes.
to tell it.
But that
Might be worth it.
that could definitely be done. I mean, it isn't done, but there's nothing in principle to stop it. It
Right.
would be fairly straightforward.
And you are just computing a derivative, aren't you? So if you've got some facilitation in your forward model which is differentiable, then you actually want to differentiate that, don't you? You've got to compute, you're actually solving another physical problem. You're computing the
No,
gradients.
you don't want to differentiate it, because the facilitator has nothing to do with physics.
Well, yeah,
it's
but
a
if your
computational
forward-
thing.
Yeah, but if your forward model has some, like obviously all our atmosphere models have some terms in it just to make it behave properly, and you're trying to run 4D var, you have to and those terms are part of the model and have to be part of the adjoint. And the adjoint is supposed it's just a way of computing a derivative, isn't it? It's not a physical model.
Why do they have to be part of the adjoint?
Yeah, well,
Why do they have to be? I mean, they're just made so you can solve the forward problem. You may need different facilitators to solve the adjoint.
I'm trying to compute the gradients of my cost function with respect to change to the input to the forward model, and therefore you can't, you have to do that. You can't. The fact that the adjoint model might look a bit strange is, well, it's not a physical model. It's a way of calculating a derivative.
And I think it's borderline to call a limiter a computational facilitator, because there is physics in that. It is representing it is representing an important aspect of the physical problem. Now we can say it's not important to be a part of the adjoint. That may or not be true, but to throw it out because it's hard to differentiate is
There's
a
a
little.
problem with something that's not differentiable, which is just a switch, but you can't. The whole method relies on
But maybe that's how the physical system works, right? We can't.
Yeah, well, that's a limitation, and there are limitations of this
For
method.
example,
Well,
in MIT case, people are just rewriting facilitators in such a way that they are differentiable. They take special
Sure,
care to
right,
write in such
right.
a way. So instead of modules, you should add some small
and some-
things and write square root.
Many of them are
and so on.
differentiable
And
almost
they are doing
anywhere, which has
this.
the interesting effect that you
That's-
end up with
that's-
a
is necessary.
formally inconsistent adjoint. And so if you do the Taylor test, that
It's
number
too
won't
much,
be 2. But if you do the Taylor test and you look at what the residual is, it will still plummet. So what that's telling you is that even with something which is differentiable only almost everywhere, you still get a lot of gradient information. It's just not consistent. And now whether or not you care comes back to the same sorts of questions about whether or not you might use a continuous adjoint. Right? There are circumstances in which you really, really, really care about the consistency of the gradient, and there are circumstances where it's less important.
Computational facilitator, that is a term I've never heard before.
You should read Max's book.
We actually have implemented and developed the same technique for finite difference codes.
You have? Oh,
Yes.
fantastic.
And we tried it out on upwind differentiation, which is a switch, right? And we modified the switch, and that one actually worked very robustly with the adjoint. So
I had the exact same experience. There's an upwinded, there's an example of an upwinding term. We take its adjoint because it's only not differentiable at one, it's differentiable almost everywhere, and in practice you don't hit that.
same
So-
goes. We also tried it out with ANO, not Wano, but real ANO that switches, and it works fine as long as you modify the switch, and it's very robust.
So often these things work out, which is good news because
If you
get
don't care about
subs-
consistency.
Well, no, even with the upwind example, it's consistent. You get second order. It's just not consistent at one point, but you don't hit that point.
It's very local,
Yeah.
so that's why you can separate it out.
Great. Anything else?
So I think to attempt to answer one of your questions, which is a bit dangerous because I'm not Hillary, one reason why OpenFOAM expresses stuff at a very high level, but strictly at compile time only. and that makes it more challenging at least. One of the things that makes this work so easily and naturally is because the full symbolic information is available at runtime. And in fact, there is a version of the Phoenix system which does all of the compilation at compile time and is integrated into C++ instead of Python. And this system just doesn't work with that because that system doesn't have the symbolic information available at runtime.
But I mean, those are things that are superable.
It's superable, but it'll always be significantly harder if you don't have the information available at runtime.
So it is a lexical analysis that is a challenge.
It's not lexical analysis that's a challenge. It's the semantic analysis of what the code does, right? Semantically analyzing and all of what the code does to get the adjoint is a much harder job than simply observing it happen as it goes, where you do no analysis, you merely record what happens. So if you have all the symbolic information available at runtime, then you can do something much, much, much easier. This is in fact a general rule, and one of the reasons why I would argue code generation is a good idea, which is analysis is very, very hard, synthesis is relatively easy. So if you can set stuff up in such a manner that you don't have to do analysis steps, then your life tends to be much easier.
Okay, thanks very much.